And just do a recap. Last time, we are in the middle of proving a theorem, the main theorem, which makes the links between the Loewner energy, SLE, and also this universal Liouville action. Let me just state it again. It will in two cases. So if the curve gamma, a Jordan curve, passes through infinity, so that would be a curve, infinite curve. Then we have that the Loewner energy of a gamma rooted at infinity equals over pi. I'm going to write it in a different way. So it's the gradient of log of f prime squared integrated against the Euclidean area measure. So f is the conformal map, h is the conformal map from the other side. So that up here from omega h star to omega star. And we've asked both f and h fixes infinity. So this is the first instance where we have that the Loewner energy, which is a priori defined through the exploration process of the curve, and you have to write down its driving function, take Dirichlet energy of this driving function, you get this quantity here. But on the right-hand side, I haven't finished writing it. I just have the sum of two terms involving these two conformal maps. And on the right-hand side, you don't see any exploration process. And in order to show this, so this would be the key. Basically, all the technical proof is inside the statement of this part, which I showed you last time. The exploration process uses heavily this additivity property. And we showed first the additivity property also satisfied by the term on the right-hand side, which is a priori not obvious. And then I went down a bit quickly, like kind of saying, okay, let's say take the driving function to be linear, and then we prove the identity for the linear driving function. Now using the additivity, we can show it for piecewise linear driving function. And in the end, we have the convergence, which I haven't shown, but at least shouldn't be too surprising that if we show the identity for piecewise linear driving function, it holds for any curve. And the second part of the theorem, which is that if gamma is bounded, you have a very similar formula. So I will use f and h again. So f from the unit disk to omega, h from d star to omega star, and I ask h of infinity equals infinity. Then I have that the Loewner energy of gamma rooted at any point is equal to 1 over pi, again gradient of log f prime square dA plus 1 over pi d star gradient h prime squared dA. And there are two more terms. So log of f prime of 0 divided by h prime of infinity. So today I'm going to show you how one can go from the first one to this second one. It should be elementary a priori, because we know that on the left-hand side, this quantity is actually Möbius invariant. So a priori, whether the curve is bounded or not, it shouldn't matter at all. But on the right-hand side, this formula seems to be very similar, but it's not actually so easy to go there to from above to here. So the goal of today I'm going to show you is that we can actually go from an intermediate step. And I'll give you a third expression of the Loewner energy in terms of the determinants of Laplacian. So let me just draw the setup here. I'm going to view my curve as a curve on the sphere. I would assume here gamma is smooth, meaning C infinity smooth. And this is a sphere inside the sphere. And I have a metric G is conformal to a metric, the round metric. So what is the round metric? So G round. You can think of just if I do the stereographic projection, mapping the sphere into the complex plane, this will be just 4 over 1 plus c squared times the Euclidean distance, Euclidean metric. And G is another metric which is conformal to this metric, round metric. And I ask sigma also to be smooth. Right, I put the round metric, but on top of it, I take another metric which is just locally a scaling of the original metric. And now my curve is somewhere here. Again, we'll call this side omega and omega star. And I will write Laplacian of, there will be 3 Laplacians. The Laplacian on the space, the whole sphere, Laplacian on each of the domain with the same metric, and assume they have a Dirichlet boundary condition. So these are Laplace operator. So it depends on the metric because you can also write this as the divergence, the usual definition of a Laplace Beltrami operator. And you can think of in order to define the divergence of the gradient, where the gradient depends on the metric, the divergence also depends on the metric. Yeah. And I say this Dirichlet boundary condition, it means that this is a Laplace operator which acts on space of function which vanishes on the boundary of omega and omega star. So the theorem. So in the same paper, we showed that if I define this quantity h gamma g is a smooth curve, is a metric conformal to the round metric. This is, I define it to be log determinant of Laplacian of the sphere. Put a zeta. I'll explain what that means later, but minus the area. So area depends on the metric of the sphere. This is the first term, minus log determinants of Laplacian of omega g minus log determinant omega dot g. Definition. It depends on gamma because both domain omega omega star depends on gamma. It depends on the metric. All the terms depends on metric. The theorem is that the first one, I called it star. We have h of gamma g equals h of gamma g round metric. So, in other words, H is Weil invariant. So like Weil invariant means like if I change my metric by multiplying by a smooth function, this quantity is still invariant. The second one is that the Loewner energy of gamma equals 12 times this H of gamma G minus H of S1 G. And this S1 is just any circle. You can take it to be an equator. Okay, so this is the another expression expressing the Loewner energy in terms of determinants of Laplacian. This one I can simplify a bit. If I take these two metrics to be the same, although I don't have to, anyway, this is Weil invariant, but if I take them to be the same, then these two terms, they doesn't depend on the omega, they will just be away, so they will be 12 times log determinants of Laplacian of the disk minus plus log that d star G minus log determinant G minus G. Okay. So why this is an expression which will allow us to bridge these two pictures. So here on the first one, we notice that infinity is a very special point. And I somehow, in order to get to the second expression, I want to move away this infinity from the curve. So it would be better to have a more intrinsic expression about each of them. And this will be the intermediate step. And this will tell you, okay, originally, if infinity is here, well, actually, if I express as on the sphere, then this point wouldn't be any different than any other point. And this is the place where it allows me to move the infinity away from the curve. Okay. Actually, it's not. This expression is not hard to show if you know the first one. So the proof of this thing will be, I'm going to show you how 1 imply a star, and I will use the star, sorry, the second double star, and this will imply 2. So let's try the G. And also, if you notice that the first, the star equation here, this will tell me that the Loewner energy, again, is Möbius invariant. So if I change my metric, apply a Möbius transformation to the sphere, then it would amount to multiply my metric by a conformal factor, a smooth function on it. And the key tool, right here. It's called a Polyakov-Alvarez formula. Right here, I haven't tell you how these determinants have been defined. This will be, I will come back to it later, so to also give you a more conceptual way to think about this determinant Laplacian by interpreting as a Brownian loop measure. But for now, let's just assume that these things are well defined, and this Polyakov-Alvarez formula, it just tells me how I can compare two different determinants of Laplacian if I change my metric by a conformal by a Weil scaling. So there will be two cases. Let me state first if the domain D has smooth boundary. So everything will be smooth in this this part. Has smooth boundary. And I have two metric, G equals exponential 2 theta of G naught. Then this Polyakov formula would tell me the log determinant of Laplacian on the domain with the new metric, so exponential 2 sigma G naught, minus log determinant of Laplacian D. With the original metric, this is equal to minus 6 pi, just the Dirichlet energy of this conformal factor plus the integral of D K, so the AG naught, KG naught. Plus the integral of boundary of D, KG naught of sigma, plus minus 1 over 4 pi integral normal derivative of sigma now G naught. Okay, let me tell you what these terms are. So here it's everything is explicit. So this is a Gauss curvature. So everything depends on the metric, and here we only use this G naught, the reference metric. So this is a Gauss curvature for the metric G naught. This is the area measure. Now this is the integral along the boundary of your domain. This term is a geodesic curvature. This is length. And this is outward normal derivative. Okay, the gradient also depends on your G naught. Okay, this is the first case. If D does not have boundary, then the same formula applies. We just replace log that by log that Laplacian of D minus log of the area of D. So this you should always think them as a single entity. I will just replace this guy by this. Yeah. Here I haven't defined what this thing. It's a notation so far. Okay. All right. So this is the Polyakov-Alvarez formula, which tells you how this log determinant changes if you change the metric, and in order to show the first one, the star equation, follows directly. For this, you have to just look at how each term they cancel out. I have a h function would be like should be think as 3 terms. So this term, this was the red term, the second term, and the third term. You just look at each of the contribution. Okay, for this, all the area integral, they would cancel out if I have a 1 integral on the whole sphere minus the 2 integral on the complement of the curve. So all the area contribution would cancel out. And here, this term would also cancel out. This term only comes from the second and third term, and the geodesic curvature, they have an opposite sign if you come from the 2 different sides of the curve. So this sum would also cancel out if you do look at the sum of the 2 guys. And the last term as well, the normal derivative, if you take the normal derivative from 2 different sides, they take opposite sign. So I think this would just follow very straightforwardly, and I think it's known like for many people. I shouldn't claim that as my result. But for the second one, let me just do it here. So now let me show you how I can get from 1 to this second star. Let me assume the metric G0 is the Euclidean metric. And now I'm thinking of my curve living on the sphere where there's the background metric G0 to be dz squared. All right, this is also dg0 here. All right, a priori, I cannot apply. So now I'm going to check. I'm going to plug in this G0 into my formula on the right-hand side, and I'm going to show that it's equal to the formula on the left board. So this is the equation 1. Sorry for. This will be the equation 2. So a priori, I cannot do this because this metric doesn't make my sphere compact. There will be a few technical difficulty if we want to apply this. We even want to define this determinants of Laplacian. But however, I'm still going to show you the proof, assuming that G0 is the Euclidean metric, which is the actual proof. I have to do it using a lot of differential geometry. You just start with a compact metric on the sphere, and you can show this, what I'm going to show you directly. But let me just show you this proof, which is you're going to see why these terms cancel out and how they come in easily. And also, this is actually not too wrong, because if you think about, I know already my functional will be a Weil invariant. You can think of, I can approximate this metric using some metric on the sphere which is compact. So that, imagine like you have your balloon, and then you kind of stretch out more and more infinity. You're going to approximate this one. So okay, let me just apply this to this. Okay, so this is my omega. This is my omega star. My determinants of Laplacian with the metric G0. I can just pull back this metric to the upper half plane. I will just write this like determinant of Laplacian in the upper half plane. Now with the metric exponential 2 sigma G0, where sigma is exactly log of f prime. Right, f is a conformal map would just say how much if you pull back the metric, this will be multiplied by f prime squared. So you get. All right, if I take the difference, I'm going to do this minus log determinant of Laplacian in the upper half plane, G naught. And this is for Polyakov-Alvarez. Let's just apply it. You get minus 1/6 pi, 1/2 integral of gradient sigma. This is log of f prime. The Euclidean metric. The Gauss curvature is 0. It's flat. It's the next term, the geodesic curvature. I'm looking at the geodesic curvature on the boundary of my domain. So it's straight. It's a 0 plus 0. And then the next term. Okay, so maybe you don't remember, but last time we actually have seen that the normal derivative of sigma, would be the geodesic curvature of f of z times f prime of z minus the geodesic curvature at z. So here would be, this is z is here. This would be k of, the curvature here is k of f of z. All right, and here there will be minus 4 pi. Now the boundary of h, you have k of fz minus, so this one is 0, so I can just leave it, length. So again, this yellow part, the yellow part, this is equal to, I can just push forward, so this you get to the boundary of omega, k, c. Right, this will be just pushing forward. Okay, this is not 0, but if you sum up two sides, summing up both, so this would tell me so this term would go away, because again, if you from one side of omega or the other side of omega, this term would just be cancelled out. So summing up both sides, you would obtain that 12 times log determinant. Okay, so I would take the minus sign, I change multiply by 12. So this would give me, you get h with g naught plus log determinant minus log determinant this is exactly 1 over pi. So this is the, well, this is not the proof for one implied double star, but not far from being proved. The only thing which is not totally correct is that this Polyakov formula doesn't work for a domain where you have an infinite, a non-compact domain. But you should, like, to the actual proof, you have to really start with a round metric and compute everything.
Nevertheless, the formula is correct.
The formula is correct. Yeah. So I think this is maybe the simplest way to get to go from here to the determinants of Laplacian. And also, you know that this determinant of Laplacian is a Weil invariant. So you can, yeah, that shouldn't be. I think this proof is not too far from being true.
Can I ask a question?
Yeah.
So, one star follows from this calculation because it doesn't depend on G.
Yeah. Well, the one star is like we discussed. You just check using Polyakov formula.
I see. So once you know that, like IL doesn't depend on G, right? Somehow, like the gamma and G have no relation to each other.
There's still some relation because gamma still sits conformally in your sphere.
But I can pick them independently of each other.
Yeah, you can pick them independently, but
the expression does not depend on G at the end.
Yeah. But still, like, it would depend on which conformal class of metric that you take. Although there's only one conformal class on the background, still, like, this conformal class will determine how your curve is embedded in your sphere.
Just one.
Yeah.
You have not totally completed things, right? You still have the determinant on H, right? So the one on H and H star.
Oh, H and H star. This would be the term here. These are these two terms.
Yeah, I understand.
Yeah.
But when you go up to the sphere case, with the determinant prime.
Yeah, right. Here I'm showing that if I take the difference of these two guys, these two terms, they will cancel. So I only need to check this equal to the Loewner energy. Yeah. Maybe the question about the metric is the independence of the gamma and G. I include the G here is actually really to help you to think about this Loewner energy being a Möbius invariant quantity. You can do, it's even Möbius invariant, it's more than Möbius invariant, it's even Weil invariant. But however, if we, from this first formula, I can show that this Loewner energy is a PSL2C invariant. This will be coming for free. Yeah. Other questions?
Maybe some like out of the blue question.
Yeah.
So it seems like what you're doing, you have some quantity that depends on gamma and on the conformal class of the metric.
Yeah.
But to compute it, you write down some path integral or something that depends on the metric. So you take some regulator and then you do this generalization by subtracting this h of S1.
Yeah.
Is this kind of what's going on?
Yeah. It's totally correct. Yeah. So this formula, I will later use this formula to relate to a Brownian loop measure. So it's a bit more intrinsic, I think, to express the Loewner energy in terms of this determinants of Laplacian, although they're actually totally equivalent. And even, to be honest, this formula has some drawbacks because I need to assume regularity on the curve. And this we will see when we define the determinants of Laplacian. There's a few assumptions on the curve you need to assume. And I guess this is also the way to tie these two expressions together. Then having this dichotomy between infinite curve and finite curve is quite awkward. Okay, let's do this, the part where 2 star imply the lower formula. Let's erase this one. Well, okay, it's exactly the same trick. Again, we assume that G naught is, let me just say, assume G naught is the dz square, but now my curve is embedded in the complex plane. Like now infinity is somewhere else. Like, or in the sphere picture, you just now put infinity here. And this is my disk. This is omega, omega star, d star. Okay, let's write in this G naught. G naught is here. G naught is also here. It goes directly. So 12 times minus 12 times log determinant of Laplacian of the G naught minus log determinant Laplacian of G naught equals minus 12 times log determinant the unit disk. Now I can pull back again. So this is exponential 2 log f prime G naught minus log determinants of Laplacian G naught. This is minus 12, 1 minus 6 pi, 1/2. Okay, integral of, this is the good term that we wanted. Okay, next term, the Gauss curvature, this is 0. The next term, the geodesic curvature. Now the geodesic curvature of this flat Euclidean metric of the unit disk on the circle, this is 1. You get 1 times log of f prime, the Euclidean length, minus 1 over 4 pi. Okay, the next term, this is sigma. This is log of f prime. Okay. Log of f prime, this is the real part of log of f. So the absolute value here, this is the real part of log of f prime, which is a holomorphic function. So the real part is a harmonic function. This is a harmonic function. This is a harmonic function. This guy equal to 2 pi 2 pi log of f prime of 0. this term, I'm taking a normal derivative of a harmonic function along the circle. And the normal derivative at each point, if I'm allowed to switch this normal derivative with the integral, this would be okay, this will be the integral of okay, am I allowed this? So this would be, if I just do without the normal derivative, I would just get a log of f prime. And here this the normal derivative, you have the length that changes, so which is actually doesn't matter. But we can still do the same trick as before. This will be the k of f of z times f prime of z minus k of z. So these two terms, is the same trick as before. If I sum up two sides, this will give you 0. So if you just have this term, you would have an integral of 1. And the outside will give -1. And here this term is a change of variable. You are going to sum up the curvature from inside of omega and outside of omega. So this term always vanishes. But now we get what we get is a
you could not use the Stokes theorem and just take the Laplacian inside with 0.
This will be 0 as well, right? Yeah, I think, yeah, right. Yeah, so even without summing up, we will get 0. Yeah. Right. So anyway, here we would get, okay, 1 over pi of this term, it'd be okay, so this will be 2 pi, so this is 4, right? And you see why there's an additional term up there. Sum up both sides. We get this second equality. Okay, so far this completes the proof. So just so the rest of today's lecture, I'm going to give you the precise definition of this determinants of Laplacian, and how that's related to the Brownian loop measure, and also how one can also guess this result from SLE considerations. Let me just start slowly, if there are questions. So we are going to move away from this theorem. So this theorem, so the rest of today is really just to give you this conceptual idea about the determinants of Laplacian and how things are connected to other things. But tomorrow, we will come back to this formula, and tomorrow's lecture we will really be focusing on the Teichmueller theory part of the story, and the only thing you need to know would be this formula. You can even forget where the Loewner energy came from, but for now we won't be talking about it anymore. Okay, so second part. So this determinants of Laplacian. Let's look at two cases. So again, always the case where you have a M, G without boundary, and D, G with a smooth boundary. So the Laplacian, the spectrum of Laplacian, here, this is, you will have 0, lambda 0, lambda 1, but actually spectrum of minus Laplacian. And here, the spectrum of a Laplacian, this is, let me put the D here, M, G. So you have 0 strictly less than lambda 1. And here I recall this spectrum here, it really means that so I have also a family of eigenfunctions, Ej, Laplacian of Ej plus lambda j, Ej equals 0, and Ej, if I restrict it to the boundary of your domain, this equals to 0. And the first eigenvalue of the Laplacian on the compact surface, this corresponds to a space of constant function. To define the determinants of Laplacian, we will use this following called the Zeta regularization. We define the Zeta function to be sum over 1 over lambda n to the power s, where I only count the non-zero eigenvalues. Therefore, when we there will be a distinction between these two. And here, so this is convergent for if the real part of S is strictly larger than 1. Here, this is a very typical behavior of if you have a, sorry, I have to assume something more, sorry. This is compact manifold. This is with finite area. So there's something called Weil's law, which tells you how many eigenvalues underneath below a certain value. So this number of eigenvalues, it grows linearly. So it's basically looking like a 1, 2, 3, 4, right? So the Zeta function, you just define it instead of the usual Zeta function, you replace this n by lambda n. Because they grow linearly, this Zeta function is absolutely convergent for positive, for the complex values, numbers with real parts larger than 1. And under assumption, the regularity assumption here, we can show that the Zeta function can be analytically continued to 0. It's holomorphic near 0, and we define minus log that of Laplacian equals, so the Zeta equals the Zeta prime. So you have an analytic function, you can take derivative at 0. And we put the prime, just notation to denote the case where we have thrown out the kernel here. So this is just notation. Okay.
So this regularity assumption is more strict than being just moved?
No. There are several cases. I think I might not be telling you the most general situation. I know if it's a C11, it's already okay. And it doesn't need to be C11, but also if you have a piecewise smooth and with an angle, it's also okay.
So it's much less strict.
It's not strict for a smooth, yeah. But we still state everything for the smooth case because a priori for Weil-Petersson, so the curve with finite Loewner energy, it's not enough. So their regularity to define this determinant of Laplacian is not enough for the Loewner energy class. So in this case, anyway, it's not going to be optimal, so we just keep it smooth. Yeah, and also the proof of a Polyakov formula you can find it's for a smooth. Also a paper by Osgood Philip Sanak. That's I should cite it actually. Osgood Philip Sanak on 80s. Okay, maybe let me explain why we call this, why we take this definition. Let me put it in quote. This is a heuristic. So let me just take a derivative in S. So this would be, I'm not able to do this, so n larger than 1. This is will be exponential minus S log lambda n. Right, I take ds. And this would be minus log lambda n multiplied by exponential minus ss log lambda n. So now if I ask it to be s equal to 0, well, of course, this expression only works if s is has real power strictly larger than 1, but still I'm going to do this. This will give you 1. So this is heuristic. Here you will give you let me just write minus log the product of all the lambda n. So it's kind of making sense that we are calling this part determinants of Laplacian. And also a side remark, I think physicists use these determinants a lot as well. They would say this determinants of Laplacian to the minus 1/2 is exactly the partition function of the Gaussian free field. So that means if I look at this is so this is the action functional of phi. Phi is a function. So thinking of we're integrating over all the phi function from D to R. And this is kind of the renormalizing factor one need to put in front in order to get the probability measure. So
it's minus delta.
yeah, right. Yeah, so I'm always taking the one with positive spectrum. Yeah. I think so. Physics actually uses a lot of determinants of Laplacian, but here we are going to really use this zeta regularized determinant, and that will be really relevant when there's interpretation of this zeta regularized determinant in terms of a Brownian loop measure. So maybe I think it's a good time to take a break, and after the break, I'm going to tell you how this zeta regularized determinant is related to the Brownian loop measure, and yeah. So the key message of the second half of today's lecture is that this determinant of Laplacian, log determinant of Laplacian, has an interpretation in terms of Brownian loop measure. So actually, in probability theory, there's a lot of quantity in complex. Coming from Brownian motion can be related to a quantity in complex analysis. For instance, we can look at the Brownian motion in 2 dimensions. Basically, you can think that it has 2 coordinates. They're just independent one-dimensional Brownian motion. So how it moves vertically and horizontally, they're totally independent, and each of them follow a one-dimensional Brownian motion. And this Brownian motion has a very good property, is that if I run the Brownian motion, I look at its trajectory, and apply a conformal map of my domain. It's a 2D thing, huh? It's if I apply conformal map, then I get another trajectory, a random trajectory. And this trajectory has exactly the same law as if I start the Brownian motion on the right-hand side. The time parameterization would not be the same, but if you just look at the trajectory itself without forgetting the parameterization, this will be the same as before. So the push forward of the Brownian motion will be a trajectory for Brownian motion. And because of this property, it, for instance, would tell us the harmonic measure on. If I want to look at the harmonic measure on the viewed from this point on the boundary, would be the harmonic measure. The harmonic measure is defined, as if I look at the map F, which sends this point to 0 and to the disk. The harmonic measure is just a pullback of the uniform measure on the circle to my domain. And the Brownian motion itself, the uniform measure is the same as the hitting measure of a Brownian motion. All right, so in order to see what is the harmonic measure here, you just look at, say, what is the harmonic measure of this part? This will be the length of this part divided by the total length. Or you can think of what is the probability of my Brownian motion starting from 0 before hitting this point, hitting the boundary at this part. And because of the conformal invariance of a Brownian motion, the harmonic measure on this curve would also be just the hitting probability of a Brownian motion starting from this point. So here you translate some objects like from either complex analysis or this harmonic measure into a it's a probabilistic interpretation. Another example is that if I look at the heat kernel, right? This is the fundamental solution to the heat equation. So this means just if I take the time derivative of this heat kernel, this will just be the Laplacian, and Pt converges as t goes to 0 to the delta xy to the delta measure the direct mass at the goes to 0. And this heat kernel, it also has interpretation in terms of the Brownian motion. So that would be this is the distribution. So the Brownian motion at time t. So the Brownian motion starting from x, and if you wait for time t and you look at the distribution of where they are, so the bt, so the probability of bt inside some set A is exactly this pt xy dy. So again, this is the, well, the heat kernel. How is that related to the Brownian motion? Or if you want, probabilist says, okay, the Brownian motion has the diffusion generator being the Laplacian. Okay. So now we are also looking at the Laplacian, and it should be connected to a Brownian motion in some way. So how we connect this? So we start from the zeta function. Okay, this is equal to sum of n 1 over lambda n to the power s. I'm going to write it in a slightly different way. This is equal to gamma of integral from 0 to infinity t to the power s minus 1. And okay, let's write this. The trace of exponential t Laplacian dt. And what is this trace of? So this is just, if you want, it just sum up exponential of t lambda n. Let me just, let's stay in the case where the domain was boundary. It's not even it's not enough. Smooth boundary. Okay, why we have this identity here? I recall it gamma of s. This is just integral of 0 to infinity. Sorry, there's a minus sign here. T to the s minus 1 exponential minus t dt. All right, if you want to compute this integral without the gamma term, you have to do a change of variable, and the change of variable will give you the power. Well, okay, you will see this lambda to the power s coming from the change of variable. All right. Okay, what is this exponential of t Laplacian? Okay, this is. So exponential of t of Laplacian. So this, if I apply to a test function, so it acts on the space of test function, this has to be equal to the integral of phi y of pt xy. Tay. Right, this is what the fundamental solution to the Laplacian it means. Let's say t. And now, but on the other hand, this side, I can also write this as, remember, I have this family of eigenfunctions. And for this spectrum, I can choose this family of eigenfunctions to be orthonormal basis for L2 of so the area measure. And here I will have, this will be phi with En. And you can act each of this operator to En. So this will be T minus T lambda n times En. Sorry, Enx. So this will be also equal to n, one goes to n infinity. What I have is just a phi y E n y exponential minus t lambda n E n x dy. Right, and now I can just identify, let me just put this guy inside. So I have this expression here. This should be true for any test function phi. So this has to be equal to pt of xy. Okay, so now if I do the following thing, the zeta Laplacian of S, this is equal to 1 over gamma of S, integral 0 to infinity, 2 to the power x minus 1, sum of exponential minus t lambda n dt. I'm going to write this thing as this is the integral on my domain D of my sum of n. I'm going to put it here inside first. Enx exponential minus t lambda n dx. Okay, what I'm not doing much. I'm just replacing each of this guy by this integral. And this integral, because En is also normal basis, this integral is just 1. And but what this guy is, so now if so this whole thing is simply the integral of the unit disk. I have pt xx dx. It's just another way to write down this trace of a heat kernel. All right, and we want to take, so this is the heuristic part. If we want to take zeta prime at 0, we notice that if you look at the expansion of 1 over gamma s, this is roughly just like, well, this expansion near 0 is s, highest order is s, as s goes to 0. So if my function, a function f of s, is holomorphic, at 0, then f of s divided by gamma of s, you take its derivative at s equal to 0, what you will get is just f of 0. If I have a s multiplied by some holomorphic function, I take its derivative at 0, I only need pick up the constant term of the thing you multiplied on. Here I have my zeta function is 1 over gamma s times something, which depends on s, which is actually not holomorphic at s equal to 0. But let's just assume it is. So this heuristic would tell us gamma, so this would be our determinant minus log determinants of Laplacian. This should be the term which is here while s is replaced by 0. Okay, s replaced by 0, what you will get is 0 to infinity, 1 over t. The next term is this integral of pt xx dx dt. This is the heuristic part. But here, then, now I'm going to interpret this guy. So PTXX, now this is a term. So this equality definitely doesn't make literal sense because if we just think about what is heat kernel, in 2 dimensions, the heat kernel is behaving like 1 over t. Okay, even without integrating this term, you would have like 1 over t squared integrated against dt, but this is not integrable. So this is definitely something which is infinite. But if you do measure theory, then you can say, okay, I don't know, infinity is a difficult thing to deal with. I come to subtraction, addition of infinity. But if I give a meaning behind of each of the terms, and then I can get infinite measure. And infinite measure, I can do a subtraction and addition, things like that. So as the comment that I did before, so this pt of xy, this will be the density function of my Brownian motion starting from x and ending at y. Here, I'm going to interpret this guy as the Brownian bubble, Brownian loop, of time length t and starting from x and coming back to the point. So it's the whole story about the Brownian loop measure. It probably doesn't develop from this way, but I'm kind of presenting the thing in the other way around. But now let me just give you the precise definition of a Brownian loop measure. I think this is due to Lawler, Schramm, and Werner. I'm formulating this in the manifold, the manifold setup. So dg a smooth domain Laplacian with Dirichlet boundary condition. And let me take Brownian motion. That would be the diffusion generated by the Laplacian on this domain. And literally, it just means it would have the distribution behaving like this heat kernel. And with the heat kernel with boundary condition, which is 0 on D. And if you want, you can think of I run my Brownian motion. It's a probability measure, okay? For each time t, this gives you a family of paths starting from x to some other point. And I'm going to throw away my Brownian motion if it hits the boundary. Okay, let me just write this, the following thing. Wtx be the measure on Brownian path starting from x killed if hits the boundary of your domain. Okay, this is a measure on a family of paths which all starts from x, and its total mass, I would denote it by this. This is a total measure. This is a number which is less than or equal to 1. And if we have such a family of paths, I can disintegrate with respect to the endpoint. By saying that there exists a family of measure such that this Wtx is integral over d with respect to the area measure of the endpoint of Wtx to y. And this is a family of measures on path from x to y staying inside in D. And what's this total mass? Total is pt xy.
So I'm a little confused about the definition of this W.
Yeah.
Is a measure on the path or on the disk or on the space of path?
On the space of path. This Wt, this is a measure on space of path.
Of paths of T? What is T?
Yeah, this is a very good question. This T is called quadratic variation. So in fact, if you run a standard Brownian motion, the time is you can read off from the path. And the path is never rectifiable. You can't compute its length, but you can take the small time cut and you look at increment and you square them, sum them up. This is almost surely equals to T.
Okay.
So this is called quadratic variation of a Brownian motion. And here we are in 2 dimensions, so the quadratic variation is actually equal to 4t. But there's an intrinsic notion of length of measure on path from x and staying inside D.
And you just declare the measure to be 0 if it hits the boundary, or?
Yeah, you just you restrict to the path. You define first the path on the whole domain, and you just restrict it to the space of path which doesn't hit the boundary. So the total mass will become smaller. If I don't restrict to the domain, this will be equal to 1.
I see. So in fact, it always less than 1.
It's always less than. It gets strictly less than 1 even.
Does it decay with T?
Sorry?
This total mass
Yeah.
as a function of T?
This one? This one? Yeah, if T goes to infinity, I think this will converge to 0. It will be, if the domain is non-polar, it's going to almost surely hit this. If you wait for time enough long in 2D, it's always going to hit it. And so this will converge to 0. Here is actually, this killing is relevant to this Dirichlet boundary condition. In fact, what I've hidden a little bit in the story there is when you do this fundamental solution, Laplacian, I'm looking at the solution for which it vanishes when x and y goes to boundary. And here, what we are actually doing is that I'm just giving this number a measure which has total mass this number. And I'm going to looking at this random object, which is the path. All right, now I have defined this guy, and this is not necessarily going to less than 1. So this integration that has the total mass is the heat kernel. So especially when T goes to 0, it's blowing up. Okay, let me just maybe. All right, the Brownian loop measure inside domain D. This is defined as the integral of 1 over T, integral of domain D. Now I'm just looking at the space of loops from x to x. Now integrate this measure dx. dt. Okay, this guy, this is a measure on a Brownian loop from x to x with total quadratic variation of 40 here. And so now you can think of if I sample my time according to this 1 over t measure, and then I sample a point on my domain according to the area measure, and then I run the Brownian loop according to this measure. So this defined for me, this is a measure on space of loops, and all the loops are inside containing T.
But I will still, since you know that the total mass is Pt, and you know that Pt diverges at t equals 0.
Yeah.
So how do you, still it makes sense this way?
Yeah, it still makes sense. So what you can say is that, for instance, you can compute things like what is the loops if I give you a domain. I have two sets. You can look at what are the total mass of loops which touches both of them. Then you can throw out the small loops. But even like this, it's like when you even say if I want to define the Lebesgue measure on the real line. I know the length is infinite. I can't sum up 1, 1, 1 infinitely many. But I still have each measure which is, if I restrict it to my interval to from minus m to m, I know this measure is finite. I can define my measure of the Levesque measure on the whole real line by making larger and larger. Here we can do the same thing. We can look at, start with loops which with t larger than epsilon. This is a totally well-defined finite loop measure. And now I'm just adding a part of an infinite measure by making t smaller and smaller and smaller. So as a measure theory point of view, you can define this infinite measure. We are totally okay with dealing with infinite measure. And now this guy is supposed to be the total mass with the, it should be related to this determinants of Laplacian, as we just.
Okay, so the secret is infinite measure.
Yeah. So, but just like without even talking about Laplacian, this guy is very interesting object. Maybe, for instance, it has two good properties. So they were showing that, I think maybe this property is probably, not sure. So this has two properties. So like this thing depends on the metric, okay? So when I run the Brownian motion depends on the metric because diffusion operator depends on the metric. Everything depends on the metric. But one can show that as a measure upon forgetting the parameterization. The measure has the same as d if I apply a Weil scaling. So both of them defines for you infinite measure on the space of loops, and the loops. If you forget about how these loops are parameterized, like there's a t, how you go from x to y. There's a time, which is given by the quadratic variation. So this thing that depends on the background metric. But if you forget about this parameterization, and also forget about which point they start, then these two measures are actually the same. This is the same thing as before I tell you, this Brownian motion, if I start from this point, if I apply a conformal map, okay, I can think of this Brownian motion with Euclidean metric on this domain as a pulling back. There will be a Brownian motion here with the conformal metric here. And they were saying, okay, this invariance that I was just telling you is saying that, okay, if I change my background metric by a conformal factor here, the trace or the trajectory of the Brownian motion you see, it has the same law as before. And here is the same thing. And this infinite measure, they're actually the same.
You could say naively, you could suggest the scaling is right because dt over t just scales, no scaling, and then a over w, the mass is pt, which is 1 over t.
Yeah.
And a, of course, scales like
t squared. Yeah.
This a is squared.
Yeah. So this is checked exactly as you said, like locally, how this behaves. The second one is that if I have d prime is inside d, and I look at mu loop of d and restrict it to the ones included in d prime. I have infinite measure, and then I throw out those loops which touches d prime. This measure is the same as d prime, which follows from the construction. Even before how you define the loop measure in d prime, you run a Brownian motion and throw it out if it hits the boundary. Here as well. Here if I make the domain smaller, I can just throw away those loops touches d prime. So this is d prime. Okay. Okay. So this is the loop measure. How we're going to relate to this determinants of Laplacian. So the following theorem, I'm going to state it for the version which is in the paper by Maureen Sam, Min J. Park, Joshua Pfeffer, and Scott Sheffield. But actually, the computation is I'm sure that people do know like this theorem, but they express this in terms of the Brownian loop measure. So the theorem is saying that if I look at the total mass of Brownian loops with a quadratic variation larger than delta inside D. So this is basically, if you want, this is the integral from delta to infinity of 1 over t pt xx d dA of x dt. This has an expansion which I need to in my notes now. Okay, the volume of, so this depends on the metric G, volume of D divided by 4 pi delta minus the length of the boundary of D for square root of pi times delta. So there it's diverging. Of course, you know this has to be blowing up, but how fast it blows up that depends on the area. So where this first order will be 1 over delta. The second order term is depending on the boundary length, and it's the order of square root of delta. And there's the next term, chi of D, the Euler characteristics, log delta plus gamma. Gamma is the Euler's constant. So this is basically 0.577. So this is a term which would appear in some derivative of the gamma function. And the next term is minus log that of the Laplacian. And the remainder is something which is going to 0. So the constant order or larger than constant order are all here. So in this way, this will be a precise statement about the total mass of Brownian loops is a renormalized. So the renormalized Brownian loops, so this term minus this term, and this term will be equal to the minus log of determinant. Okay, if I want to prove this, it's actually it's not complicated. But for this, everything is captured in how this term. So there's a trace of heat kernel, small time expansion of the trace of the heat kernel.
But in a way, I mean, that was known for a long time.
Yeah. This is they just express this in terms of a Brownian loop.
That's right. Because the one is not.
Yeah, this is after all, it's a computation of this guy. But with this, because of this interpretation of Brownian loops, we can do things a bit nicer. give some geometric meaning of several things. I can keep this one. Okay, corollary. If you have, let's say, this is my domain D, this is K1, K2, everything smooth. I can ask about what is the Brownian loop measure. So what is the measure of the loops touching both K1 and K2? So this would be, before in that expression, we know like the small loops will contribute to this blowing up phenomenon of the loop measure. But here, there is a chance of total mass of loops will be finite. All right, okay, let's then just say, okay, this will be a limit of delta going to 0 of the same thing, lub D loops touching, I would denote it by K1, just K1, K2, to say that it hits K1 and K2, and the quadratic variation is larger than delta, for delta. So here this is for delta, 2 equals exactly this term. I'm just saying, okay, this will be a limit if I truncate less and less. This will be a limit when delta goes to 0. Okay, how I can write this? The loops touching both of them, I will write this as a Brownian loops of D, just quadradiction, very larger than 4 delta. All the loops in D larger than 4 delta minus mu loop. Now it would be D minus K1, those contained in outside of K1, also quadratic variation that is larger than 4 delta, minus K2, quadratic variation larger than 4 delta, plus mu loop K1. I'm throwing away those loops which doesn't touch K1, and then I throw away loops which doesn't touches K2. But for those who touches neither of them, I had been throwing out twice, so I add them back. Right. This is just inclusion-exclusion sum. All right, and then you can just expand, before taking the limit, you expand everything here. And you will see actually all these 3 terms, they would cancel out. Yeah?
Why would we choose 4 delta?
4 delta is exactly this time parameterization in Brownian motion.
But
So
I would have 2 delta because it's t for each direction. So.
yeah, but here, usually the Brownian motion has diffusion Laplacian over 2. So here it's actually a Brownian motion going faster than, yeah. Yeah, basically this quadratic variation is just the time when you actually run a Brownian motion. Yeah, so, well, the volume, you can check that if I do the sum and differences, they will be exactly canceling out, and the length as well. And the Euler characteristics, you have to check it. compute each of them, they also cancel out this. And in the end, in fact, you just get the constant term here, and the delta goes to 0. Actually, doesn't really matter. Oops, I'll run out of. So in the end, you get minus log determinant of Laplacian of d plus log that d minus k1 plus log that d minus k2 minus log that Laplacian d minus k1 including k2. And everything is rigorous now. The story is just saying, as long if my Brownian loops, I'm counting the loops which is finite, which total mass is finite, then I can express them safely as determinants of Laplacian. And in this way, this equality between the total mass of Brownian loops and the determinants of Laplacian is precise. So this determinants of Laplacian has a lot of interpretation. Like before we showed this is a partition function of Gaussian free field. And here with this determinants of Laplacian, it's with the Brownian loop measure is particularly nice if we really consider what is entering the Zeta regularization. As what I showed you, like even in this Zeta computation, this particular way of regularizing is rather telling you something about the Brownian loop measure. And finally, coming back a little to the SLE and the Loewner energy story. So before, the result I was showing you is that basically the Loewner energy is this h 12 times h of gamma g minus something, the normalizing term from the circle. And what this was log that of the sphere minus log that omega minus log that omega star. So this can be interpreted if we just interpret log that minus log that as total mass of Brownian loop measure. This will be interpreted minus 12 times or Brownian loop measure on the sphere, loops touching gamma. Again, this quote mark is here because this loop measure is infinite. So, but still, you can think of this heuristic. This is the way I think about the Loewner energy.
Wait. Your Loewner energy of gamma was well defined. Right?
It's well defined, yeah.
And so, what happens to?
So here it's like
to do to give some meaning to the mu loop.
Yeah. So there's a way, like for instance, using this formula, we can see like it will blow up like a length of the curve with for some square root of delta. If you throw out this term, and there's some term coming from this gamma term, and then the remainder is the Loewner energy.
So there is a renormalized version of the mu loop,
yeah,
which gives you the result.
Yeah, gives you the result. But this renormalization, I wouldn't think is very crucial because in the end we will be considering the Loewner energy. Like you think that's a quantity which compares the loop on the sphere versus the loops in other domains, and then you subtract. Then, although we are subtracting infinity. But then still, the total mass of loops touching the two sets will be finite. Let me just show you one example related to in SLE literature. So I think this idea probably should trace back to Kontsevich, Suhoff, and also Werner and LSW. Yeah, is that they also think of SLE as quantities as a measure on simple loops which satisfy a certain conformal restriction property. But the guiding, it's very heuristic. Okay, I should also cite it's made rigorous by Shen. For the following version, so is that we should interpret SLE loop measure as a measure on simple loop which has some gamma, which has the density exponential of C kappa over 2 times Brownian loops measure on the sphere touching gamma. I might be off by a sign. Let's see. Yes, I'm off by a sign. So what does that mean? What does it? It means. Okay, maybe let me take SLE loop in a domain. So this would be a measure of SLE loop. Domain D. There's some measure on SLE loop contained in the domain D. By the way, the A third, well, okay, let me should write kappa equals 3 kappa minus 8, 6 minus kappa over 2 kappa. And this is a central charge associated to SLE. And in the case when kappa is A third, this is a central charge is 0. Here you were just saying, kind of saying, having a uniform measure on space of loops, and this curve would be the outer boundary of your Brownian loop measure if D is simply connected. But okay, what did things doesn't quite make sense yet. For instance, here you are looking at the space of loops, which is there should be infinity. This is total mass of loops touching gamma. But if I'm allowed, if I assume this is true, but then I can say, okay, if I change my domain, so now my D, this is my D prime. This is A. Then I can write this Radon-Nikodym derivative of my SLE. Then this philosophy implies, okay, the measure mu SLE inside D prime SLE kappa for each gamma, well, their density will be proportional to exponential minus c kappa over 2 mu loops. Sorry, here, if I looking at D, this will be the mu loops in D, mu loop. So in D prime over gamma minus mu D loop gamma. These are infinite, but if you think about this infinite measure behind, now I take the difference in between. This will be the total mass of loops which touches this part, both of them, which is finite. And this is equal to, so there will be mu loop in D touching both gamma and D minus D prime. And what Dapon has shown is that also this, I think this is also, this idea is from Kontsevich, an early work of Wendelin there about conformal restriction property is exactly similar to this form. It's saying the measure of SLE in a bigger domain versus a smaller domain, they're absolutely continuous with respect to each other. I'm missing the integrator function gamma should be inside D prime. But then this weight is given by the total mass of loops which touches your curve and the set that you are taking out. And this is a finite thing and everything makes sense. And this can be actually proved. This is basically saying, like, giving a meaning to this heuristics, why we can interpret SLE loop as a density like this.
So this SLE was you pick a domain and then you're looking at loops. So you're looking at where is gamma in this picture? Is whatever.
Yeah, gamma will be this curve. Gamma is this curve. Yeah, sorry. Yeah. Yeah. I didn't really present how the SLE loop is defined, but so this part is really heuristic. What I've shown before was the SLE in the caudal case. For the caudal case, it has a similar interpretation, but you would have to add boundary terms as well. So it's a little bit more complicated. And the loop case, you can. It's a bit like how I define the loop energy, which you are shrinking the points. Yeah, shrink it. And then you can restrict it to some other domain. And in the loop case, the good point is that there's no boundary point and it's a bit cleaner. But here, you can see also why 12 in the Loewner energy would appear. So if I just look at this central charge, when kappa goes to 0, what I have is minus 24 over kappa, right? And then if it's so this will be 12 over kappa.
Sorry, I missed what K was. What was K again?
Kappa.
Kappa? Yeah, kappa is in the SLE. So SLE is so some random fractal curve, which is yeah.
Sorry, this is a real number.
It's a real number. It's a kappa is strictly larger or equal to 0.
And what does it tell you?
So yeah, right. So it's in the first lecture, but roughly speaking, is that a simple curve, you can encode each of this Jordan curve into some real value driving function. It's a function, in the loop case, it will be a function from R to R. This is called the driving function of the loop. And if I take the driving function to be square root of kappa times the Brownian motion, one-dimensional Brownian motion, this will give you some random fractal curve. And this is called SLE kappa. And when kappa is 0, this is a circle. When kappa is less than 4, it's almost surely a simple loop. And if Actually, yeah. So we are looking at a small kappa case. And this Loewner energy has interpretation as the large deviation rate function of the loop energy. Basically, that would be the term which is its density, and you look at the part which is above kappa. So here we should have a minus here, so the energy would be minus 12 loop measure, which is also what is written above there. Yeah, sorry, I'm running over time, and thanks for your attention. Yeah.